it's my pleasure to discuss with you some of our recent progress on Hamiltonian simulation. So my talk today will be based on the joint work with Ling, who is the organizer, and also Dong, he will be giving another talk tomorrow. So here is the outline of my talk. Basically, we are going to discuss what is highly oscillatory dynamics, and then what is the major questions and challenge we were able to provide answers or partial answers to. And then we discuss what is our algorithm, and interestingly, we observe this so-called superconvergence behavior in our algorithm. So let's get started. I guess to this audience, it's not very unfamiliar what is a Hamiltonian simulation problem. So let me just quickly run through the definition. First of all, we have certain descriptions of the Hamiltonian, could be time-dependent, h of t. Then we can write out the Schrödinger equation with an initial condition. So the task of Hamiltonian simulation is the fact that we want to construct an approximate unitary up to certain certain precision, that is what we call epsilon, when measuring in certain norm. When the problem is time independent, it's very easy to just write down the closed form of the exact time evolution. That is just going to be a matrix exponential. In the time dependent world, however, we will have an integral and then we will have a time ordering. However, all of the story remains the same. So I'm going to say that, in fact, the difficulties of a Hamiltonian simulation problem actually increases as the underlying unitaries become highly oscillatory. So in this sentence, I'd better tell you three things. Number one, what is highly oscillatory? Number two, why should we care? Number three, why do we say this is more difficult? So highly oscillatory can actually come from two different sources. Number one is, let's say, suppose this norm of h, operator norm of h, is super large. Then in the time independent case, you can see that this unitary is sort of rotating very fast. A second source that we can also see is in the time dependent case. Suppose this h itself is changing very fast, then it also gave you some highly oscillatory behavior. Then you should ask, why should we care? Well, let me just give you some fancy graph. So this, on the right-hand side, you can see a lattice Hamiltonian with large lattice number, and this is a quantum control with ultra-fast laser. On the left-hand side is the molecular dynamics, the nuclei wave functions, and so on and so forth. All of these systems are highly oscillatory, so highly oscillatory dynamics are basically everywhere. That's why we care. Now let's talk about how does this norm, which is highly oscillatory, the norm of h, come into the play of the cost. So let's look at the time-independent Hamiltonian simulation. We know that there are many algorithms out there. Majority can be split into 4 different categories: the Trotter algorithm, LCU type, and QSVT type, and the randomized protocol. So as you can see, out of all of the 4 different types of algorithm, Trotter is the only algorithm in the time-independent cases can give us this nice commutator bound. While the other 3 also all gave you this cost that is scaling in the operator norm in a linear fashion. So as this operator norm of h become larger, the underlying unitary become more and more highly oscillatory. Indeed, this we need more and more cost in order to simulate this task. Well, so we know that this commutator can give you really nice cancellation. So this is a very good feature to have if you have this first highly oscillatory source. So it's a very natural question to ask that if we are in a time-dependent Hamiltonian simulation cases, can we also explore this commutator scaling, such as the Trotter in the time-independent case? So basically, we want to construct some commutators as this kind. Additional challenge I need to bring to your attention for the time-dependent Hamiltonian, as we have introduced at the very beginning, is that it can come with another highly oscillatory source. It's the Hamiltonian itself with respect to t may be changing very fast. How do we think about this? Well, let's take an example in the interaction picture. For example, this A can be fast forwardable. However, the norm of A is very large. So if this gave you a time-dependent Hamiltonian that is writing around very, very fast. Now let's talk about the corresponding Hamiltonian simulation algorithm already exists to handle this time-dependent cases. Well, there are also different types of algorithm. First of all, we indeed have Trotter. We can do Trotter as well for time-dependent Hamiltonian. The idea is very similar to the time-independent Hamiltonian simulation. What you do is you do H1, you do H2. However, because this H is changing inside of each time interval, you want to choose this tau J, which is some time in between this short interval according to Suzuki construction, and then you compute it. So very unfortunately, this will lead to a result where your number of unitary will depend on the derivative of the Hamiltonian. Actually, if you consider higher order trotter, the standard trotter algorithm, it will depend on higher order derivatives. So as your Hamiltonians become more and more highly oscillatory, these highly oscillations will give you a large overhead if you use trotter algorithm. This issue has been addressed by two different ways. We can design randomized algorithm. The idea is that we are going to random sample the time and then break it into product formula. These are sort of low accuracy algorithm. Majority, they are first order accuracy. And there are also other ways such as the LCU-based Dyson series algorithm. Both of these two algorithms will be able to suppress the derivative dependence. That's fantastic. However, none of them give you the commutator scaling. You may wonder, we talk about interaction picture, you may wonder how does this algorithm perform when we apply them to the interaction picture. So first of all, interaction picture is having a very large derivative because of the oscillation. So the trotterization is immediately ruled out. We know that for Dyson series, when we apply to the interaction picture, it has the best asymptotic scaling. Unfortunately, it may suffer from a large overhead due to the time ordering as this pre-constant. This issue was recently addressed by one of the work by Nathan Weeb and their collaborators designing hybridized methods utilize some randomized protocol, and these algorithms were able to achieve a first order accuracy. So now it's a good time to summarize what are our challenges and what we want. So basically, in the highly oscillatory world, there are two challenges. First is that the norm of H itself is large. The second is that H itself is changing rapidly. Two desirable features correspondingly we really want to have is, first of all, we want to have commutator scaling, such as time-independent trotter. And we also want to have weak dependence on the derivatives, such as randomized or Dyson-based method. The true question here is really that can we have both? So we are human beings. That's the mean that greediness is basically written in our DNA. So if we really are living in an ideal world, let's ask ourselves, let's make a wish list of an algorithm in the time-dependent case that we want to have. So here is our my wish list, contains 4 different things. First of all, we hope the algorithm is easy to implement. Second of all, we hope it has commutator scaling, so deal with the first oscillation. Third, hopefully it's a weak dependence on the derivative used with the second kind of oscillation. And we also hope it hopefully can give high orders, or at least there is some hope to generate higher order accuracy. Now, this is in an ideal list. It's indeed too much to ask. At the very beginning, we should at least have some starting point. So our starting point is that we are going to forget about high order just for a moment. Let's see whether we can fulfill the first 3 tasks, even if we are designing some low order algorithm. Then our answer is yes, indeed, we propose an algorithm that is called quantum highly oscillatory protocol, in short qHOP, that are specifically tailored to deal with this highly oscillatory dynamics. Our algorithm is easy to implement and have up to second order accuracy. Let's see precisely how our algorithm were able to check these boxes. So first of all, yes, it's easy to implement. There is no time clocking or time ordering related units. Second, in the high precision limit, it indeed have commutator scaling. Third, it is log dependence on the derivative. And lastly, although we know that we cannot, it's not easy to get a higher order generalization, maybe you want to ask, can we at least go beyond, say, the randomized protocol, which gave you a first order? And the answer is also positive. We were able to observe the superconvergence results in the Schrödinger equation simulation, yielding a surprising second order convergence rate. This is way beyond this is definitely beyond the first order convergence. So this is a quick summary of what we were able to achieve in the algorithm. All right. So now let's discuss about in the time, the crucial part here is really that in the time-dependent case, we want to sort of explore this commutator scaling. We know that in the time-independent world, trotter is sufficient to do that task. Now you may want to ask, what about time-dependent world? We said that time-dependent, this trotter gave you bad derivative dependency. Maybe this, however, maybe it still retains the commutator bound. Well, let me just take this very simple example, which is just a controlled form Hamiltonian. Suppose the standard trotter really gave you a commutator bound. Then let's imagine I pull out a H1 and H2, suppose they commute with each other, the commutator scaling will immediately tells you there should be no error. So if you write on your run the numerics, you will see, say, a machine precision. So we did that numerics, immediately it tells you it's not machine precision that you see. So this immediately tells us standard trotter in the time-dependent world will not give you a commutator bound. Now, then you may wonder, well, if I can generalize this trotter in the time-dependent world, then maybe I can get a commutator bound. These are the so-called generalized trotter algorithm, generalized trotter formula. Yes, in this case, it's the idea is really similar to the standard trotter. You want to do H1 and then you want to do H2. Yes, you indeed returns this commutator scaling. However, I want to highlight, I want to point out, this is actually not an algorithm yet. You look at the left-hand side, then you look at the right-hand side. All that you are doing right now is that we are turning one time-dependent Hamiltonian simulation problem into two other time-dependent sub-Hamiltonian simulation problem, which still need to implement. So this, it returns the commutator bound, but it's not an algorithm yet. So now let's look at our work, how we were able to handle this issue. So just from that side, you can see that this time ordering is really something that is sort of bothering. So that's just sit around and naively think, okay, it's a problematic, let's just throw it away. So that's exactly what we did. We are, first of all, we threw away this time ordering. So this, I want to make several remarks. Number one is that this actually can be viewed as a first order truncation of the Magnus series, which turns the time ordering problem into a no time ordering problem. You can certainly get a higher order truncation, which gave you some hope to create higher order algorithm. The second remark I want to make is that after you drop this time ordering, essentially the time-dependent Hamiltonian simulation problem really is just going to be a quadrature, a numerical quadrature problem of taking this integral. Well, there are many different ways you can work out this numerical quadrature problem. For example, standard trotter would be I pick a specific time inside of this short interval, and I just simulate that time. As we have seen before, if you use this way, you immediately lose the commutator bound. There are also other ways proposed by Pauline Soma and their collaborators, such as using the randomized protocol. We want to use Monte Carlo sampling, draw a number of samples from the time, and then turn it into a product formula. Once you turn it into a product formula, then the number of costs will be linearly in terms of how many samples you draw. So that's not exactly what we are doing here. So how do we deal with this numerical quadrature? We are just going to use the most dubious numerical quadrature technique that is out there. So basically this line, what I'm saying here is that from this short interval Tn to Tn plus 1, I'm going to chop it into very small pieces, and I'm just going to do a rectangular quadrature, add up all of these rectangles. This is also called Riemann sum. I'm going to use this to use m different quadrature points to do this. Now, if this is the case, you may certainly want to ask me, isn't that you said that this H can be highly oscillatory? If that is the case, if you really want to calculate this numerical quadrature accurately, isn't that you need a very, very large number of m? How are you possibly able to simulate that? Well, luckily, it's not really a big issue if we simulate it on quantum computers, because we have this nice LCU lemma. What is m? M is the number of quadrature points that we are using here. It is also how many terms you are making the sum. LCU lemma tells us we can essentially bring this m dependence in the logarithmic factor. I want to highlight that this is also the most intrinsically quantum part in our algorithm, because this cannot be efficiently simulated on a classical computer, because it will give you a polynomial dependence in terms of m, where is m is the quadrature point. So we personally would like to think about this as a quantum Hamiltonian simulation algorithm. The first quantum come from we bring down the exponentially large Hilbert space. The second quantum part is essentially here, where we are bringing down the logarithmic with respect to the quadrature point. Okay. The second remark I want to just quickly to mention is that this idea really resembles in the classical numerical analysis, this so-called multi-scale integrator, where you have a large time delta t, and inside of this each of the truncated interval, you do some sort of things that is differently. In the end, I also want to remark that after doing this numerical quadrature, we will be successfully turning this time-dependent problem into a time-independent problem. And then we are able to use this the best scaling algorithms such as QSVT and OAA of this amplitude amplification to directly simulate this dynamics. All right, so now we have two questions. Whenever we have an algorithm, people, you want to ask yourself, how do you implement? Is it easy to implement? Second, what are the approximation errors? These answers to the two together will give us the query complexity. So let's look at them one by one. First of all, how do you implement? Well, we said that we are going to make use of this LCU lemma, but it's worth pointing out since all of these weights are uniform. So it's not a complicated LCU. It's just a very simple type of LCU. We just need to do hard mode on both sides. The second question is, how do we deal with this approximation error? There are two approximations has been made here. First is we drop the time ordering. The second is we deal with the numerical quadrature. So it turns out when we drop the time ordering, we will be able to return this commutator bound. So this is essentially where we get the commutator bound from. Second error that we are making coming from this numerical quadrature. I want to draw your attention to this M. As you can see that due to LCU lemma, our algorithm is logarithmic dependence on M. So we can afford to choose a very large number of quadrature points, making this M very large to outbalance the errors coming from here. This is also a good point to remark that in the standard charter, however, you don't choose a large number of M. Instead, you just choose one number of M. That's why the second part of numerical quadrature error cannot be balanced out. You will lose the commutator bound because of the derivative dependence. All right, so now let's look at the query complexity. So here is our query complexity as was claimed. This is a first order accuracy algorithm up to now, and we indeed have the commutator scaling in high precision limit. And you may wonder, where does this derivative appear? Well, this derivative got absorbed into the logarithmic factor thanks to LCU. So this is what we have. Now let's talk about our algorithm then applied to interaction picture. Let me first just briefly discuss what is the idea of the interaction picture. Interaction picture typically deals with a Hamiltonian, which can be separated into two parts. We have A and B, where the norm of A is much larger than norm of B. Then what you can do is that we can use this by low and B for this interaction sort of a rotation frame. What we want to do is we change this problem into another interaction simulation problem where this HI is the new Hamiltonian description we want to deal with. It becomes time dependent and it have A's unitaries about A, so it is highly oscillatory. You may wonder, why is this any good? If we take a look at of the operator norm of H, then you see that the norm is essentially B, which is much smaller compared to the original Hamiltonian description, which is a sum of both A and B. Well, does this bring you actual difficulties? Certainly, because as you can see, you are basically trading off this first oscillatory source into the second oscillatory source. Instead, you are creating a fast oscillating dynamics that you need to simulate. Well, our algorithm is catered for this task to deal with highly oscillatory dynamics. So let's talk about how our algorithm were able to perform. So here I'm taking A plus B for simplicity. I would like to mention our algorithm also work if I have A plus B T being time dependent, or even we have a scalar in front of the A where A is fast forwardable. So here is a circuit which gave you a block encoding of the Hamiltonian, then you can continue to deal with QSVP circuits. And corresponding, you may wonder, what is the approximation error? We have similar types of approximation error as before, dropping the time ordering and the numerical quadrature. As you can see in the numerical quadrature, indeed, you still have some A appearing here, but don't worry, as we said, we have LCU. This whole part will essentially go inside of the logarithmic cost. There's another point I want to draw to this commutator scaling. As you can see that this commutator essentially becomes a local commutator, where this S is just from the interval from negative H to H. So you are no longer having a global commutator to estimate. For the global error, we only have a local commutator to estimate. Okay, now it's a good time to discuss about the Schrodinger equation. I claim that our algorithm, when applying to the digital simulation of Schrodinger equation, can actually achieve this superconvergence. So what is the digital simulation of Schrodinger equation? It has many names in literature. It's sometimes called unbounded simulation, sometimes called real space simulation, sometimes also called first quantization simulation. The underlying task is basically the following. I have Laplacian, which is an unbounded operator, plus b. Well, Laplacian is unbounded, so if we talk about the norm of h, it's going to be infinity. However, we can certainly discretize the Laplacian, and here is what we get. Suppose we use just this as a very simple illustration. Suppose we use n number of bases or n spatial grid points. Then you can see that the matrix size will be n by n. Very unfortunately, if you measure the operator norm of this matrix, you see it's a capital letter n squared. However, we know that the number of qubits is in the logarithmic scale. So if you imagine yourself is the qubits, from the qubits perspective, this norm of the Hamiltonian is exponentially large, which really predominates the error. So that's the issue I really need to deal with. You may want to say that, okay, so if the norm of h is very large, don't we just say that we can use commutator scaling to get very nice cancellation? So let's try to, and this is indeed a time-independent Hamiltonian simulation problem. So let's just try to use Trotter and get commutator cancellation. Well, this is what you will get. Indeed, we tried that, and we indeed have commutator scaling. However, if you work out this algebra very carefully, you will see that this commutator scaling will still give you some independence in the norm, which is exponentially large from the qubits perspective. So this commutator scaling indeed gave you nice cancellation, but it's not sufficient. It turns out we were able to fix this issue by looking at a different measurement of the error. We were able to prove that if there is a good regularity in the initial condition, then taking the initial condition into account, instead of measuring the operator norm, instead we measure the so-called vector norm. Using this vector norm analysis, we were able to get an independent vector norm scaling. So you no longer have this exponentially large prefactor. However, it is still of people's interest trying to get an independent operator norm scaling. That's where the interaction picture will come into the play. So that now let's take interaction picture together with our new algorithm, this qHOP, and see how it performs. So the error is, there are two parts of the error. The numerical quadrature error, as we said, will go inside of log. So let's ignore that for a moment. This part of the commutator error is essentially coming from dropping the time ordering. So let's just focus on this commutator error and see whether we can get n independence. Immediately, yes, the answer would be yes, you can get n independence. So I have this h, which gave us a first order accuracy. And it's very easy to bound this commutator in terms of n, where n is the potential itself. We no longer have derivative. So this will give you n, which is a number of grid independent pre-error constant. So indeed, you can get n independent operator error estimate, but what you can achieve is only a first order accuracy. However, what I want to claim here for our algorithm is much stronger. It's much stronger. So our claim is going to be, for our algorithm, in fact, applying to this case, it will be of second order accuracy. And very importantly, the pre-constant is going to be independent of n, where n is the number of bases. This is the so-called superconvergence behavior, because the first algorithm achieves the surprising second order accuracy. Well, you may, so basically what I want to prove is essentially utilize this local commutator structure. I want to be able to extract another h so that to make this algorithm a second order accuracy convergence. And I also want to prove that whatever that is left over should be something that is independent of a, independent of the derivative, so that I get an independent error bounds. Okay, so indeed, this is doable. This may sound too much to ask, but indeed, this is doable. This was proposed in one of our recent work. As you can see from this local commutator, we were able to extract another h, which brings this first order algorithm into second order convergence. And for whatever pre-constant in the front, we were able to show that it only depends on V, which is B. So you no longer have this spatial grace dependency. Well, let's see how is this possible. You may wonder, it really sounds too good to be true. So just to show you some numerical results, give you some confidence, this is indeed possible. As you can see, you have a S dependence coming out linearly. And as you change H, the pre-constant essentially really does not depend on H. Okay. So now let's discuss how extremely high level, how you can actually prove it. Well, here we have this local commutator. And I want to get a second order accuracy. Then maybe you will just want to say that D, isn't that, I can get it immediately. And here is how I'm going to do it. Well, you have some expansions. I'm just going to do Taylor expansion. Well, great. Once you do Taylor expansion, first order term, which is BB, they cancel each other out. Then you are left with the second order term, which is B and the commutator AB and the S coming out. Isn't that you said if I have another S coming out, which is H, then I will have a second order accuracy. This argument is indeed correct. So it's no surprise at all our algorithm can achieve second order accuracy. But the superconvergence result is surprising. It's because this argument will still give you some independence. However, we were able to prove that the pre-constant is independent of n. This is very important. The pre-constant is actually independent of n. But this is indeed a very good time to make a remark. So first of all, this naive argument, if you truncate the Taylor series, truncate some series, it's not going to be sufficient. Second of all, is that if you look at this commutator, it really reminds you of the second order Trotter formula, for example. If you think about the second order Trotter, it depends on the Nasse commutator. So essentially, there are two commutators that are going to appear in the error bounds. Here, in the DD order term, we only have one of them. And notice that this AAB is, which is the one does not appear, actually has a higher scaling with respect to the number of grades. So we don't have the larger sort of Nasse commutator. This is sort of a nice feature to observe in our algorithm. Okay, now let's talk about, this is a fake approach. It will not give us any independent error bounds. Let me talk about on a high level how we were able to figure this out to prove the pre-constant is actually independent of n. So it really lies in, it turns out there are many different ways you can wrap things around. There are truncated, there are Taylor expansions, there are BCH formula, there are say Ziesenhaus formula, which all involve certain types of truncation. You try them all, none of them will work. None of them will give you an independent n dependence. So what we did instead is really this idea borrowing from applied mathematics, that is so-called this pseudo-differential calculus. So the idea is the following: for any of this space function, which is a function of both x and t, we can do this so-called quantization. Well, this may sound something that is less familiar, but let me just try to translate in our familiar language. So this, just visualize this quantization, which is a pseudo-differential operator, this OP as your hat. So if I have position, the hat, which is a position operator, is just a multiplication. If I have momentum, the momentum operator is just going to be negative I with a derivative. So apparently, if we look at the second term in this commutator, it has some multiplications, it has some derivative. If you work out this whole calculation really carefully, you will see that it is actually a quantization of the following phase function. This is exact. There's no truncation of any sort of series. This whole thing is exact. Then you can go ahead and plug in this quantization into the local commutator scaling that we are having. Then this is what we have. So basically what we have is this V algebra of two quantum operators. If you are familiar with this semi-classical intuition, it's a very natural analogy telling us that the D algebra of quantum operator is basically almost have a natural analogy as the boson brackets of the classical phase function. So this is not how exactly it works in the proof, but on a high level idea, this is almost what is going on in the proof. So this V algebra, you can make an analogy into this Poisson bracket. What does Poisson bracket do? It takes a number of p derivative, a number of x derivative. So what you are left with is taking the x derivative on the first term. When you take the p derivative on the second term, you can see that due to the chain rule, you get another s out. This is where we were able to create a second order convergence. And then you look at all of these pre-constants. These pre-constants are going to be bounded if the potential we are dealing with is bounded together with its derivative. So indeed, using this argument, we were able to show on a rigorous level, our algorithm is second order accuracy, and very importantly, the pre-constant is independent of n. So this is our superconvergence result. Okay, so this is just to show you some numerical evidence. As you can see, our algorithm, as you comparing to our algorithm with Trotter, second order Trotter, both algorithms give you second order accuracy. However, our algorithm, as you change, you enlarge the basis size n, it do not change the pre-constant. This is exactly what we have shown in the previous slides. Okay, now it's a good time to remark our algorithm's connection with Trotter. If you remember what I said at the very beginning, I said if I were able to generalize Trotter, then I can get a commutator bound. Is our algorithm intrinsically a generalization of Trotter? The answer is actually yes. So if we look at the interaction picture, I'm not going to work out the details. Remember, our algorithm is using this Riemann sum as the quadrature. However, you can use other types of quadrature, such as midpoint quadrature rule. If you work out this linear algebra very carefully, you will see large cancellation. In the end, what you get is half application of A, full application of B, half application of A, and you repeat this. What is this? This is exactly a second order Trotter formula. Similarly, if we use the endpoint quadrature rule, you will see that working out the algebra, we get a first order Trotter formula. Okay, so now let me summarize what I have done. We propose a simple algorithm that is called qHOP. This algorithm is very simple to implement, and to our knowledge, this is also the first algorithm that simultaneously have the commutator scaling in high precision limit and remains insensitive to the fast oscillation of the Hamiltonian itself. When applying to interaction picture, our algorithm can indeed be viewed as a generalization of first and second order Trotter. And very interesting and also surprisingly, our algorithm is able to achieve the second order convergence, which have a pre-constant independent of n in the Schrodinger dynamics. So let me just quickly remark on the future work. So first of all, I'm very interested in so here what I were able to show is the superconvergence being applied to this Schrodinger dynamic simulation. Where we have Laplacian plus potential. You may, I'm also very interested in, is there a more general criteria, say for spin system, transverse Ising, Haber model, is there a general criteria of A and B such that I can propose, also observe this superconvergence behavior? And also, is there a better argument or simpler argument? Here we use this pseudo-differential calculus. Is there a simple arguments to justify the similar kind of superconvergence? The second is that we are also very interested. Remember our wish list. At the end of the wish list is a high order construction. We are also very interested in see whether we can push this low order algorithm into arbitrary high order. There's some hope there. The reason is that remember, our algorithm dropping this time ordering is a first truncation series. High truncations of magnet series give you some hope to construct high order algorithm. So here is our conjecture. The conjecture is that I can construct a arbitrary high order algorithm, and this new algorithm using truncated magnets hopefully still give you the commutator scaling. And the practical perspective, I'm also interested in seeing arbitrary low order truncation and see, for example, if I truncate the second order magnets, can we observe a superconvergence? Actually, we observe this numerically. Second magnets actually give you a false order superconvergence result, and this proof is hopefully it will not be a conjecture very soon. And lastly, I'm also interested in seeing how our algorithm perform in practical setup and also working out explicitly the dependence on the dimension. So with that, I want to thank you for your attention, but please allow to give me just 1 more minute. I want to make a little advertisement. So we will have a IPAM long program in 2023 fall. There will be four workshops. I will be organizing the first workshop on the topic of quantum algorithm for scientific computing. We recently have a very nice lecture notes written by Lin, just appeared on arXiv. So I will, if you are interested in this material, I recommend you to take a look at of the lecture notes. And also I hope and I look forward to see many of us in this workshop. With that, I want to thank you for your attention.